Hello, my dear friend Vicky. How are you? You're muted, sorry. It's good to see you all. I was just with the children of Future Hope India. Let me introduce everyone since we're a small group and I'm recording this session. Hunter is connected from home on the island of Molokai. Shujata and the students of Future Hope, I was on the same island as Vicky and Hunter just 24 hours ago. In fact, it's Sunday night here. On Saturday night, we were all together. We had a nice potluck dinner. We went out and looked at the stars. Hunter is a student at the school that Vicky runs, and Shujata runs the school that is, oh, thank you. So Shujata runs a wonderful school called Future Hope. And we have others connecting. So Yale is one of my students from, hey Yale, how are you? I'm going to actually, hey Evan. Since we're just starting, I figured I would, before I share my screen with the VNC and all that, Evan, I see you got a very good spectrum. I'm seeing that on the VNC. You're welcome to, in fact, I'll ask Carlos. Carlos is sitting right behind me. I'll ask him to introduce himself as well. I'm going to turn my virtual thing off. You should be audible now.
Yeah. Can you hear me? Yeah. So I'm Carlos Alvarez. I'm the Keck staff astronomer that is supporting the observations tonight. So I'm helping Evan and Raja with the instrument setup and making sure that the observations are fine. And I'm here available in case something goes wrong to help fixing it if I can.
Just by Carlos being here, nothing is going to go wrong.
That's the hope.
Evan, you want to say a little bit about yourself, please?
Sure. My name is Evan Kirby. I'm a professor at the University of Notre Dame. I have been using Keck since the year 2004. Specifically this instrument that we're using, the one that you see on the screen. It's called DEIMOS, the Deep Energy Multi-Object Spectrograph.
I haven't shared my screen, Evan, so but I will soon.
But a little bit about me, I came to astronomy at a young age from just looking up at the sky and hearing people like Raja give very convincing talks about how cool the cosmos are. Raja gave an amazing talk on the island of Molokai yesterday at a school called the Akaula School. Vicky Newberry is a teacher at that school and she's online today. And Raja gave an amazing talk about his work there. And seeing similar talks like that, it just encouraged me as a child to learn more about astronomy and eventually pursue it as a career. I got my PhD with Raja in the year 2009. He was my PhD advisor. He convinced me to come to the University of California, Santa Cruz to study. And I liked Raja so much that I chose not only to go to UC Santa Cruz, but to choose him as my PhD advisor. And it was the best decision I've ever made. And Raja taught me how to use the instrument that we're using tonight. And I love the instrument so much that I'm actually leading an upgrade for it. It's now a 21-year-old instrument. So that means that it's time to give it a little makeover. And that's exactly what we're going to be doing with it. So it's still an excellent instrument. We still use it today, but it'll be even better in 2 years when we upgrade it. Tonight, we're observing right now a galaxy called Barnard's Galaxy. Barnard's Galaxy is 1.2 million light years away. Even though it's really far away, we can still see individual stars inside of the galaxy. So a lot of images that you see of galaxies, they're just fuzzy clouds of light. This particular galaxy is close enough that we can see individual stars inside of it. And in fact, we're getting a picture of every one of those stars, right? Not every one of those stars. We're getting a picture of about 100 of those stars right now. But it's a special kind of picture where we take the light of the star and we make a rainbow out of it. This is called spectroscopy. And the nature of the spectrum can tell us a lot about the star. It can tell us how fast it's moving towards us or away from us. And it can tell us what the star is made of. And that's actually what I'm really, really interested in. I'm interested in to know what the stars in the universe are made out of. How much iron do they have? How much magnesium do they have? I like to pick elements in the periodic table and see if I can measure them in stars to figure out how much of that element is in the universe and where that element came from. And that's what I'm doing with Barnard's galaxy today.
And after this, you look at some of the galaxies that are orbiting Andromeda, right?
That's right. Yeah. Actually, I'm only looking at Barnard's galaxy because it's one of my favorite galaxies, and I had a little time to do it today. As you may know, you can't see any given star in the sky at any given time. You have to wait for the stars to rise or wait for the stars to set. And right now, we're waiting for the Andromeda galaxy to rise high enough in the sky where we can observe it. And so the star that, the next galaxy that we're going to be observing is called Andromeda 18. It is in the direction of the galaxy Andromeda. It's in the constellation called Andromeda, but it is actually not, this galaxy that's called Andromeda 18 actually is not associated with the large galaxy Andromeda. It's actually much farther away than the Andromeda galaxy. This particular galaxy, Andromeda 18, is almost 4 million light years away. And even though it's so far away, we can still see individual stars in it. We can still get a spectrum of those individual stars. And I'm interested in the same questions for Andromeda 18 that I am for Barnard's galaxy. What are the stars made of? How are they moving around? What are the stars that exploded to make the elements that live in Andromeda 18?
Beautiful. Where are you with the exposure sequence? I'll share my screen, but before I thought I wouldn't. I'll start sharing only after we do a few more introductions, but where are you with your 3 20-minute exposures?
Right now, I'm finishing up the last of 3 exposures. This particular exposure is 27 minutes long, and we're just about 15 minutes into it.
Okay. 27 minutes long, so you're doing a total of 81 minutes for the 3.
Around that, yeah.
Okay. I would love to hear an introduction from Kolkata from Future Hope. Sujata, if you have a moment to introduce the school and yourself and the students, that would be lovely. If you have a moment.
Nice to meet you, and thank you for allowing us to join this program, Shadow the Scientist. I'm going to ask one of our children to introduce Future Hope School and say a couple of sentences on Future Hope School. So anybody wants to introduce who you are? Come on. You talk a lot, otherwise in class. Yes. Sadhana, come so you can be seen. Yes.
Very good morning, everyone. I'm Sandhana Shaw. I study in class 11. So this is our future of school, and we are nearly it's 33 or 31 years we are celebrating, and we are good at playing sports. We play various sports like rugby, cricket, hockey, etc. And we are winners of rugby and football in our Kolkata.
Very good.
And we want to thank you for inviting us for this helpful program. I hope we could learn something from you all.
Thank you very much. I appreciate that you're taking the time away from classroom time and time with your regular teachers to be with us. What is your favorite subject in school?
My favorite subject is English. I like to study English.
Okay. English literature, different authors, or creative writing and those kinds of things?
I think I like grammar, like the language part, writing more than literature.
Gotcha. Yeah, and Evan, just to put this in context, when we studied English and at that age, we had 2 separate English subjects. One was English language, one was English literature. One was learning the language by practicing your writing and practicing understanding grammar, and the other was, it was strange, it was separated into those 2 parts, and the other was reading other people's writing and doing critical analysis. And that was more than about language itself. It was about context and understanding why Shakespeare wrote what he did, what kind of social commentary it was, or why Dylan Thomas wrote what he wrote, and so on. Thank you. Thank you. Let's see. Yael, do you have a moment to introduce yourself, please? I mean, say, you're a high school student, just like the students in Future Hope India, but you're halfway around the world from them. Please go ahead. Tell us a little bit about.
Hi, I'm Yael. I'm a junior in the Bay Area right now. I started working with Raja through his SIP program, the summer program. I did Astronomy 18 this summer, and now I'm interning with him for the rest of the year.
I want to make a couple of translations here. When you say junior year, that's the same as class 11.
Yeah.
For the students of Future Hope, right? Because I think there you go from kindergarten to class 10, you take an exam at the end of class 10, and then classes 11 and 12 are then lead up to another exam, like an O level and an A level. But I hadn't heard the terms freshmen, sophomore, junior, and senior neither in the context of high school nor in the context of college when I was a student. So
yeah, it took a while to get. In Israel, we actually just used letters, and then 11th and 12th grade are like 10A and 10B instead of 11 and 12.
Oh wow!
It's a very different system.
I lived in an apartment building that had 28 flats, very close to where the school is located, and because of superstition, flat number 12 was followed by flat number 12A and then 14, because 13 is an unlucky number. So Yael, you studied in Israel, is it? For part of your middle school?
Yeah, I moved here like pretty early on, but I had a couple of years at school there.
I see. Where in Israel?
I lived in Netanya. It's like 20 minutes north of Tel Aviv.
Oh, north of Tel Aviv. Okay, so I know Haifa is much further north.
Yeah.
I
kind of like in between.
I see. Let's see, Dr. Shipa, you're connected from Botswana, I think. Would you mind saying a little about yourself, and feel free to turn on your video if that works for you. Yes, go ahead, please.
Oh, greetings.
Greetings.
Oh, thank you very much.
Thank you for connecting again.
Yes. What do you want me to say?
Please tell us a little bit about yourself. I know Vicky connected you to Shadow the Scientist. I seem to recall that.
Yes.
Vicky has sent you a greeting on the chat.
Oh, hello. Yes. Ever since that time.
Tell us. So you're connected to the Astronomical Society of Botswana, if I remember correctly.
Yes. I'm a member of the committee there.
I see. And do I remember correctly that you are associated with BIUST? Is it the?
BIUST.
Yeah, what does BIUST stand for? Botswana?
International University of Science and Technology.
That's what the SNT are. And what is IU, International University?
Yes, International University. But I'm not with them.
I see.
They are a different institution. I'm from University of Botswana.
You're from the University of Botswana. Okay. What stage of your studies or academic journey are you in? Are you a teacher there?
Yes, I'm a lecturer. I'm into theoretical physics.
I see.
So here I teach things like mathematical methods for year 3, year 4, and postgraduate studies. Also statistical mechanics, level 100 physics and stuff like that. But
I see.
in terms of research, I'm just a theoretical physicist. I work on a number of different fields, quantum mechanics, string theory, general relativity, and stuff like that.
Wow.
They the guy who is induced. Well, I have a couple of collaborators induced, but I think the person you were referring to is Marongwe, who is into quantum gravity.
And he is at
That
BIUSD.
Yes, he's doing his PhD in induced.
I see. No, thank you for connecting again, Dr. Shipa. I know you've connected before, and this time we're using a different instrument, a different telescope, different science than the last time. Last time we were looking at variable stars in the Andromeda galaxy using the Shane telescope at Lake Observatory. That was a 3-meter telescope. Tonight we are using a 10-meter. Hunter and Walker are brothers, as far as I remember, and Evan and Vicky and I were with them just yesterday, snorkeling in the morning and then eating dinner together and stargazing. So Hunter and Walker, in whichever order, do you want to say a few words very quickly to introduce yourself? And James, I haven't forgotten about you. I will go to you next. And Vicky, I haven't forgotten about you either. So Hunter, why don't you take it away?
Hello, my name is Hunter. I live on Molokai. I go to Akula School, and yeah, my brother's here. Yep. As you notice, it's a bit dark out. And yeah, glad to be here.
Are you sitting outdoors, Hunter?
No, I'm actually like on my bed right now.
Okay. It is late at night. It is late.
Hunter, if you go outside and you look straight up and just a little bit to the south, you'll see the same thing that we're looking at with the Keck telescope right now.
Oh, that's cool. Oh,
Walker, how about you?
Hello. My name is Walker. I'm Hunter's brother. I go to Akula, and yeah, and I'm really happy to be here, honored to learn about space too, and yeah.
I know you're very interested in space, Walker, from all your questions you were asking us yesterday. That's wonderful. Thank you for taking some time off on a weeknight.
You're welcome.
Thank you. Vicky, if you wanted to say a little bit about the school, that would be amazing. And thank you for connecting us, not just to the students of Akula, but also to the wonderful people of Botswana, many people in Botswana.
Well, definitely first, Demora, it's nice to be talking to Botswana too. I miss my second home. My second home is outside of Maun, so I hope on one trip I'll be able to get down to Gaborone and meet with you folks. Akula School is almost 20 years old now. The co-founding teacher and myself were out of the public school system during the time of No Child Left Behind, when education became pretty didactic, not inquiry approach, and we missed the inquiry, project-based learning, and some of the things that we'd learned that worked with students. So we started the school, a small school, 40 students, grades 5 through 12. Hunter's a junior and Walker's in 8th grade. Very diverse interests. So we kind of, we jump on what opportunities come our way. And through Ohana Kilahoku, we found Shadow the Scientist. And it's been a wonderful part of our lives. And we've Zoomed with Raja over the past year several times, and Uncle Raja to the kids. Yeah, we're so grateful for his friendship, for his patience with our students and with us as educators. And I'll probably beg out a little early tonight, Raj. I don't know about you, but I'm really tired.
Well, that seems like a dream to us, you know. We were, Evan and I were just saying that can't believe that earlier today we were on two different islands. We were on Molokai, we were on Maui for a couple of hours. We hijacked a conference room at the airport.
Okay.
Just to hang out there and work. But no worries, Evan. I know you have to get on to the next galaxy. You have to do I wonder if I should share my screen, because Evan is going to now point to a different galaxy, and Carlos is going to join him in the next room. So James, I haven't forgotten about you. Vicky, thank you. So I'm going to put my headset back on since Carlos is no longer in the room. I wanted him to be able to hear you. Just a moment.
While you're doing that, can I do one quick shout out to Future Hope of India? I'm an English teacher, and I love that you like grammar. I teach grammar, which is such a challenge in a community where English is basically a second dialect. So thank you.
Thank you.
And I'm sharing my screen, so I didn't want to make sure that you got to see what I'm seeing. So before I forget, James, if you wouldn't mind taking a moment to introduce yourself. I seem to remember you're an amateur astronomer. Is that the basis of your interest in Shadow the Scientist?
I am actually a student.
Oh, you're a student,
Yes, I go to the University of Hawaii at Yale U.
Oh, fantastic.
So I'm about just 40 miles away from Keck.
Oh, fantastic.
And I'm an astronomy major, and I look like I'm a bit of a straggler on here because you guys are all interconnected.
No, we're not.
Just saw what was going on.
We're not actually that connected. We're, so you are a student of Heather Kaluna's, I'm guessing.
I just saw this online, at random. So I just dropped in, wanted to see what it's about. I'm excited to learn.
And one of your professors, Heather Kaluna, when she was an undergraduate, she worked with me in California, and she and I collaborate on a bunch of outreach-related things. You're seeing a bunch of screens.
I'm actually from California.
You are? Okay. Which part?
Yes. I am from Orange, California, so just south of Los Angeles.
I know exactly where that is. You're not far from Anaheim and Disneyland and all those kinds of good places. Yeah. Wonderful.
I wasn't accepted in Santa Cruz, so now I'm here.
Oh, I'm sorry.
No worries.
I'm so glad you're connected. I'm so glad you're connected. Yeah, we love it in Hawaii also.
Thank you for having me.
Sorry, what was that, James?
I said thank you for having me.
Oh, you're most welcome. You're very welcome. This is Shadow the Scientist is for all, certainly for everyone. And that's the beauty of it. There are literally people from all over the world joined onto today's Zoom call. And we have the Future Hope group from Kolkata, which is a city I grew up in. We have you from Hilo, but you also represent California. Hunter and Walker from Molokai, Vicky in Molokai. We have Dr. Shipa from Botswana. So, Yael, I was going to say that I've just been in email contact with Yuting. I sent you're on an email I just sent, and he's going to point me to some RLRs. So near the end of tonight and the beginning and ends of the next 9 nights, we'll get repeat spectra of some of the stars that if you want to say a little bit about your research project to the group, that would be amazing.
Yeah, so my research group studies RLI ray stars in the Milky Way, I believe. We calculate, their distances, periods, just everything to do with them. How much should I say about the specific
I think
papers?
the group may not know what an RLI star is. Ivan does, Carlos does, but the rest of the group may not know.
RLI rays are a specific type of variable star, which is just a star that changes in brightness with a certain pattern. The RLI rays are very reliable in their pattern, which allows us to calculate things like their distance very easily and very reliably over time. Their pattern is pretty quick. So one astronomer can watch the entire thing and then calculate things based off of that instead of having to wait like hundreds of years for it to get back to the same position it was earlier. All of that makes them really, really good stars for calculating distance, which is like the base of everything else that needs to be calculated in astronomy.
And so these things pulse over, the full pulsation cycle might last anywhere from 6 to 18 hours. So we will, and you're right, they're all within our galaxy. The RLRE you're studying are all within our galaxy. One of the people who is involved in this observing run recently published a journal article about RLRE in the satellite galaxies of Andromeda. And he used Hubble Space Telescope images to do that study. Now, Yael, the RLRE you study, one of the reasons they change brightness is because they get bigger and smaller over time. They progress. I mean, they expand for a bit, then they contract for a bit, they expand again, and the time it takes between from one instance of maximal size to the next instance of maximal size is what you call a period. When it reaches its maximal size, it also reaches maximum brightness, and that the time period between its maximum brightness and the next episode of its maximum brightness is called the period. And yeah, as you were saying, it's a short amount of time, 6 to 18 hours. One of the cool things is when these stars expand, the surface of the star is actually, the front surface of the star is moving towards us. And because the front surface of the star is moving towards us, the velocity of the star appears to change. Overall center of mass of the star's velocity hasn't changed, but just the surface from which we're getting light, its velocity changes. And that's one of the things we're trying to monitor. I'm actually going to stop sharing and start resharing, because I realize I'm not sharing sound, and I want you to hear the sounds of the observatory. So give me a moment. I'm going to stop sharing. And when I reshare, I'll share with sound. By the way, at any point, like right now, would be a great time for you to ask me any questions about, or ask Yael any questions about the research you just talked about, anything at all. Let's see. Let me see if I can bring up the Zoom.
Yeah, I'm calculating those velocities, which are called redshifts when they're moving away from us and blue shifts when they're moving towards us. It was like a really major thing that we did this summer. Actually, we used software that Evan Kirby wrote like a decade ago for all of our data processing. It was really cool.
Thank you. Yeah, I'm trying to see if I can see all of you on Zoom. I'm not seeing the people. What's happened to the... Can you all see me?
Yes.
Yep, see you.
Where is all the Zoom video gone? I'm so lost. I'm going to stop and start resharing again. Sorry about that. Now I can see you all, but what happens when I... Oh, let me try this again. Yeah, participant can see my screen. That's great, but I can't see the participants. I can see the names of the participants, but oh well. So what you should be seeing a window here in which you see a bunch of controls. This is controlling the DEIMOS spectrograph. Some of the spectra you looked at were from the DEIMOS spectrograph, some were from ESI. You're looking at the controls of the DEIMOS spectrograph here. And I will show you a few other screens here. Let me see if this one, okay. Can you all see my cursor as I draw a circle?
Yeah, we can see it.
You can, okay. This thing on the left of the screen that looks like an image with a split screen, the lower part looking brighter than the upper part. This is an instantaneous image of the night sky. Every white dot is a star. You can see some really faint stars, but you can also see bright stars. And the reason the lower part looks brighter than the upper part is the lower part is actually a piece of shiny glass. It's a mirror, whereas the upper part is just a polished piece of metal And as you know, polished metal in general is not as reflective, doesn't reflect light as efficiently as polished glass, polished and silvered glass. So this lower part, this lower narrower rectangle is a mirror. And even though the night sky is the same brightness throughout, it looks brighter in the mirror because the mirror is more reflective. And then the upper part is a reflection of a metal plate, aluminum plate. And you'll notice that there's a small box around a star. And to the future hope children, remember how I was explaining that as the Earth rotates, you have to rotate the telescope equal and opposite to the Earth's rotation to make sure that the night sky is not, that the telescope is looking at the same patch of night sky at all times. And this particular star with the square on it is something called a guide star. It's the telescope. We are using this star to guide the telescope so that the guide star doesn't move. It doesn't, the pixels on which its light is landing doesn't change with time. We're using it to make sure that the telescope's rotation is perfectly precise so that that star remains frozen on a particular set of pixels. If we notice that from one image to another image 1 second later, that the light of the pixels, the light of the star has drifted from one set of pixels to the neighboring one, the system knows to apply a small correction to the telescope to nudge it back into its original location. So that's, you're looking at relatively bright stars, but it may surprise you to know that these stars, even though they look very bright to this telescope, they're too faint to be seen with our eyes. With just our plain eyes, without binoculars or telescopes, these stars are too faint to be seen. They are, roughly speaking, they're about 20th magnitude. I'll tell you how the magnitude system works. The faintest stars you can see, not from Kolkata because there's so much light pollution, but if you go outside Kolkata to a place like Shantiniketan, if you go outside to a place like Molokai, away from the city lights of Waimea or Hilo or Kona, if you go out into the countryside in Botswana, what you see, the faintest stars you see are about 5th magnitude, number 5. The magnitude system is a logarithmic system, and some of you are studying logarithms in mathematics. So it's an inverted logarithmic system. So if a star is 5th magnitude, it's just barely bright enough for us to see. If it's magnitude 0 or magnitude 1, then it's much brighter than the 5th magnitude star. In fact, a magnitude 0 is about the brightest stars we see in the sky. Planets are brighter than that. The moon is brighter, of course, but the brightest stars we see are about 0. Now, if I go to 10th magnitude, those stars are 100 times fainter than the faintest stars we can see. So every 5 magnitudes, every step of 5 magnitudes is a factor of 100 brighter. So a 10th magnitude star is a factor of 100 times fainter than the faintest stars our eye can see from a dark site. So 5th magnitude star, magnitude 5 stars are the faintest things our eye can see. So 10th magnitude star is 100 times fainter. What about a 20th magnitude star? How much fainter is it than the eye can see? Okay, so this is a question for the group. How much fainter is a 20th magnitude star than the faintest star your eyes can see? So how do you get from 5 to 20? You have to add 3 5s to 5th magnitude to get to 20th. And each time you add 5 magnitudes, it's like making the star 100 times fainter. So you have to do that 3 times. 100 multiplied by 100 multiplied by 100 means the stars you're looking at on the screen are about 1,000,000 times fainter than the faintest stars the eye can see. But because this is a 10-meter eyeball, this telescope is like a 10-meter eyeball, these stars are very easily seen by this telescope. Before I keep talking further, any questions about what you've heard so far?
Any question?
Yeah.
Yeah. Come here and ask the question.
Yeah, please, I can hear you. Please go ahead.
Not have any direction, north, south like that. So how you understand that which direction? I know that how you calculate anything like
You cut out. Could you please repeat the question one more time? The audio cut out. Sorry. I heard north-south. I heard, yeah.
Space do not have any direction, right?
What doesn't have any direction?
Outer space.
There is direction. It's not, we are not traveling through outer space, right? We have to look at the positions of the stars. And of course, there is a north, east, southwest directions in the sky. In fact, if you look at this, what's called a compass rose that I'm circling my cursor around, you'll see there's an arrow pointing to the east and there's an arrow pointing to the north. So this that's the orientation of the sky right here. That is, in other words, if you go in this direction to the lower right, that's going further and further north in the sky. And if you go in this direction, like my cursor is going, then you're going further and further east. Now you'll notice it's rotated. North is not up, east is not. If north were up, would east be left or right? If north were up on a map, would east be left or right? If you look at a map of India, or you look at a map of the world, you look at a map
Right.
of east would be right? But here, if you rotate these green arrows so that north is pointed up, can you see that east would be pointed to the left? Can you see that? In other words, if you take these two arrows, and if you rotate them counterclockwise, anticlockwise first by 45 degrees and then by another 90 degrees, north would now be pointed up, and east, after 45 degrees rotation, would be there. And then now 90-degree rotation would be pointed to the left. Do you see that? Do you think we've made a mistake, or is that strange? That in space, when you look at the sky, if north is up, east is to the left, whereas when we look at a map of the Earth, if north is up, east is to the right. And Yael, I can't remember if I explained this to your group or not, why this is the case. Did I?
I don't believe you did.
Okay. Here's why. Let me explain. So again, just to repeat the phenomenon, if you look on a map of the world or a map of any country, if you have an arrow with north pointing up, east is indeed to the right. I mean, if you think about it, if you draw a map of India, you have an arrow pointing from the center of India towards Kashmir, that would be pointed north. And you have another arrow pointed from the center of India towards Kolkata, that's pointed east. And Kolkata is to the right of center, and Kashmir is to above center. So if north is up, east is to the right. On the sky, if north is up, east is to the left. Here's why. When you look at the Earth, you're looking at a globe from the outside. You're looking at a sphere from the outside, right? We were just using the basketball as an analog for the Earth. When you look at maps of the Earth, you're looking at a sphere from the outside. When you look at the sky, you're looking at a sphere from the inside. Right? It's called the celestial sphere. I mean, it's an imaginary sphere because the stars are not all located on one surface, but from their appearance, they look like they're on the surface of a sphere and we're at the center of that sphere. So there's a parity inversion when you look at a sphere from the outside versus the inside. Let me explain what I mean by parity inversion. I'm sitting in an office right now. In the office, there's a door. And I'm sure for the students who are sitting in a classroom, or if you're sitting at home, there's a door to your classroom. Is there a window on your door? Can I ask this question? Is there a window on the door of your classroom at Future Hope? Glass window, okay. Now, what is the name of the room you're in? Is there a classroom number, or is there a number to the classroom or a name? What's the name of your classroom? I'll tell you where I'm going with this.
It is a library.
Library, okay. So suppose you wrote the word library on the outside of your door so that when someone is entering the room, they know they're entering the library. And let's say they wrote it on the window part of the door, the glass part. Okay, they just wrote an L for library. If you look at that same L from the inside of the room, it would look parity inverted, right? From the outside, it would look like this. From the inside, it would look like that. That's like the north and east arrows. If you look at the north and east arrows on the surface of the Earth, north is up, east is to the right. But if you, that's because you're looking at the sphere from the outside. But if you look at the same sphere from the inside, you'll see a parity reversal. North is up, east is to the left. This is something astronomers get used to, but that's the explanation.
Understood.
Heather, I wanted you to introduce yourself. You have a lovely background. Heather is actually on the summit of Maunakea. Hey, Heather.
Hey, Raja.
How are you, Heather? We have groups from all over the world. I'll introduce them in a moment, but please go ahead and tell everyone who you are and what you're doing. You're on the summit of Maunakea.
Well, I'm Heather, and I'm the telescope operator. My whole job tonight is to basically do I mean, at the basis, I'm just moving the telescope, but I'm also keeping an eye on the weather. I'm keeping an eye on all the instruments. I have to fix things if they break. I'm basically the first and last line of defense at night up here. So, yeah.
Heather, your altitude is 14,000 feet, right?
Approximately. I think we're just a few
under.
hundred short, maybe.
Yeah. And at that altitude, there's much lower oxygen content in the air than at sea level. And you have oxygen tanks around you. You're not using one right now, but you do have them around you.
Yeah, there's a condenser right next to me that I can put on at any point. Okay. And we do have some liquid oxygen, though. We're a little short until delivery tomorrow, so I'm conserving it.
And my understanding is you and the others who work on the summit of Maunakea, you don't sleep on that mountaintop. You come down to the 9,000 foot level, and that's where the living quarters are.
Yep, we have bedrooms, a canteen where there's some cooks to make us breakfast and dinner while we sleep. So
there's a ping pong table. There's a ping pong table and a pool table.
There's a pool table. There's a TV with some satellite TV on it.
It's very strange playing table tennis at 9,000 feet. The ball moves very differently through the air because there's less air resistance.
Well, that's probably why I'm bad at it. So. But amazingly, pool's not that hard at that altitude, even though you're thinking a little harder with a little less oxygen.
Heather, so I know there was a threat of fog at the beginning of the night. How is the humidity? I guess it's showing up on one of the monitors, right? I'm going to share my screen again.
14% right now, so.
Okay, and that's on this monitor that you're seeing here where it says MET, it's at 14%. Am I pointing to the correct red and blue lines? I don't know if you can see my screen, Heather.
Yep, the blue is the outside and the red is inside my dome.
Inside, okay. And they're below 20%, they're just below 15%, in fact. And is it above 80 that we need to start worrying about closing?
Sort of. We work by dew point differential, which is what those numbers,
on the
they're
right
kind of like the green numbers. It's basically 24, almost 25 degrees Celsius until the dew point, which means no chance of us hitting it. But once we start approaching within 2 degrees Celsius of the dew point, we do have to close, unless we see fog, in which case we close anyway, because it probably means it's on the way.
I see. And one of the things you told us at the beginning of the night is the air quality today is very, very good. That is, the stars are not twinkling very much. Seeing is very good, half an arc second. Is that still the case?
It seems to be. I haven't gotten a focus update in a bit. That's the definite way to tell. But what I'm getting from, we have a monitor on the True Summit, which is near some of the other telescopes. It's called the DIM monitor, and it takes data of the stars constantly overhead to try to determine what the seeing's like, and it's reading about half an arc second still. So I think we're about in that range.
I see. So there are 4 screens that we're looking at. So this is one of the screens, VNC. This is tel status. It's telling us the status of the telescope. By the way, this is telling you where the telescope is pointed. These are like the longitude and latitude of the coordinates of the sky where the telescope is pointed. And you see it says and 18A, and stands for Andromeda, 18A. 18 and 18 is the name of the galaxy. A because it's a particular piece of metal that Evan is using to isolate particular stars. LST is the coordinates that are directly overhead at the moment. And that's changing because as the Earth spins, different coordinates are changing at the rate of 1 second per second. And this is units of hours, minutes, and seconds. LST stands for local sidereal time. UT is Greenwich Mean Time. That's also changing at the rate of 1 second per second. And it says it's September 19th. It's September 19th in India. It's September 18th in Hawaii, but in Greenwich Mean Time or Universal Time, that's what UT stands for. It is already September 19th. The other things have to do with, again, the pointing of the telescope, the elevation and azimuth, how the dome that houses the telescope is, how it's situated, how it's oriented right now, things like that. There's a lot of numbers here. I won't go through all of them. I don't know if I can go through all of them. I don't know what all of the numbers are. But but basically, this screen is showing us the status of the telescope, including how it's pointing. This graph in red is showing us how blurry or sharp the image of a star is. The lower it is, the sharper the image is. This is something called the full width at half maximum of the star in units of arc seconds. An arc second, you all know what a degree is. 90 degrees make up a right angle. And the 1/60th of a degree is an arc minute, and 1/60th of an arc second, 1/60th of an arc minute is called an arc second. And you can see that currently, which is the current time is on the far right here, 2052 means it's 8:52 p.m. here in Hawaii. And you can see that the full width half maximum is a little under 1 arc second, which is good. This is lower the better. Then the other screens, there are 4 screens. This is one more set of screens. This is something, this window on the left is what's used to make sure that the telescope is pointed just right. And we are taking spectra of stars that you'll see on the next screen. These spectra will appear in just a minute because Evan is taking a long exposure. You can see, in fact, right now, that he is taking an 1800 second exposure. And if you do the math, 1800 is exactly half an hour, because 1800 seconds is exactly half an hour. 1800 seconds, remember? An hour is 3600 seconds, because it's 60 multiplied by 60 minutes in an hour and 60 seconds in a minute. And this clock is counting up. It's saying that it's finished 1066, 67, 68 seconds out of 1800. This is giving you the percentage of time that's elapsed. This is the total exposure time is 1800 seconds, and it says that it is completed nearly 2/3 of that, 60% of that. It's taking a spectrum right now and of not one star, but multiple stars in Andromeda 18A. Any questions? Let me pause here and see what questions you may have. And again, I can cycle through the 4 screens. This is where the spectra will appear after the 1800 seconds have elapsed. This again is controlling exactly how you point the mask, align the mask, and this is really pointing at what the telescope is doing. Okay, any questions at all? Please feel free to unmute, and we're a small enough group that we just have 11 connections here so that we can easily, you can easily unmute and ask. Any questions at all? And I know Vicky had to sign off because it's she has to wake up early tomorrow, but can you all hear me okay when I'm speaking? Hi, Aparajito. It's good to see you.
I can hear you.
Oh, very good, very good.
Other than fog, what are some other things that could cause the observatory to shut down? Because like in California we had all of the smog from the fire. Is that a problem in Hawaii?
That can be a problem from the volcano, from fires, certainly.
We did have to actually shut down for a wildfire recently. there was a large fire down at the Pahaloloa base camp. And we have new dust monitors that we were testing out, and they were in the range. So we closed and waited till it calmed down. So yeah, we can have fog from the volcano and smoke from below cause a problem. Humidity, fog, high winds, snow, all those things can do it. Earthquake, of course.
Right. Aparajita, do you want to take a moment to introduce yourself? And I think Richardson, we haven't asked you to introduce yourself. Feel free to. Aparajita, take it away. And Heather, I hope I'm not keeping you from anything.
Hi, everyone. My name is Aparajita Bhattacharya, and I'm from India. I completed my master's in physics last year from St. Xavier's College, Kolkata. And I work with Raja, and I actually work with Keck II data. We mainly try to extract ISM spectrum, which is the spectrum of interstellar medium, which is kind of like the stuff that lies between the stars in these giant star-forming galaxies. And yeah, we do a bunch of different things with that spectrum.
Thanks, Aparajita. Richardson, did you want to take a moment to introduce yourself, please? And again, only if you're in a place where you can talk. While we're waiting for Richardson, Aparajita, I have been going over 2D spectra and some relic slits with Evan. We haven't gone over in detail the really extreme case that you sent. I intend to do that. I'm also supposed to meet with Deborah in person in Hilo to go over relics and ideally reduce some of the same slits with pipette to see if those features survive using a different reduction software. So I just wanted to give you that update. I did get your email about that you sent today. I'm really backlogged with my email. I will try to answer that. But I think the relic slit that I shared with Evan today was a new relic slit that I've just found in one of the M33 masks, and it was very clear over there that the spatial character of H alpha and sulfur 2 and nitrogen 2 were different from that of the rare lines. In fact, there's a pair of other lines whose spatial character is the same as H alpha, sulfur 2, nitrogen 2, but the rest of the lines have a different spatial character.
Okay.
So let me just go back to the screen that we were looking at here. And yeah, tomorrow and tomorrow night when we run Shadow the Scientist 8 to 10, even before that, I'm hoping we'll get some RLR spectra of some of the same ones that that you've already been monitoring, just to get more time points on those. So this is up to thanks. This is up to 78%. So you can see that in another 400 seconds, so a little over 6 minutes, 7 minutes, this will be done, and it will read out, and then I can show you what spectrum looks like from the what half an hour of exposure time produces for these stars in Andromeda 18A. I'm proudly wearing this t-shirt today, a sweatshirt today. It was a gift of the Akaula school given to me last night by the students. So Evan got one and I got one. And I really need it. It's cold in Waimea. You'd think Hawaii is warm, but Waimea is rainy and cold. To the students at Future Hope, we're throwing a lot of information your way about telescopes, spectra, but we will, over time, I will and others will explain what we're doing, why we're doing it. Happy to answer any questions you have at this point or any point really later in time also is fine. But if you have questions right now, feel free to ask. If you say, what is that window showing? Why is it doing this? Those are perfectly fine questions to ask. There's no bad questions. They're all good questions. Could you hear that sound, by the way?
Yeah.
I have a question.
Yeah, that sound was an alarm
clock.
saying that the exposure, something is, some instrument. There we go. It sounds like a cuckoo clock, but it's some notification. Sorry, Walker, you were going to ask a question. Please go ahead.
We are showing.
How many telescopes are on Maunakea?
Ask your question again, Walker.
How many telescopes on Maunakea were you working at?
About 20.
Oh, that's a bunch.
Yeah, a bunch of telescopes. Sorry, one of the students from Future Hope was going to ask a question. Please ask.
In your screen, I can see like cross correlation. What does that show?
Cross correlation over here. That's a wonderful question. Okay. Cross correlation is a fancy word for matching patterns. Let me explain how it's being used over here. But in our everyday lives, cross correlation is used in many, many, many things. Okay. Maybe I should start by explaining that first before I explain what you're seeing on the screen. Many of you have heard of the company Google. Have you ever done a Google search by typing in a word? You have? Is there a computer open in front of you, or is there a smartphone open in front of you where you can do a Google search right now? Okay. Why don't you put in your favorite word? If you put in Future Hope Rugby, if you put that in, there's some, if you type any word like that, any word into a search bar, there's actually some fancy cross correlation going on. Basically, what the system is doing is taking the words you've typed in and it's looking for that exact pattern of words in documents. And how do we search for patterns? If we were doing this by eye, if I wrote the word future and someone gave me a newspaper and said, where are the words future written in this newspaper? What I could do is take a transparent piece of paper in which I've written the word future, and I could slide that over the newspaper until if I see the actual word future there, it'll line up perfectly with the writing on the transparent piece. That's an example of cross correlation. I'm looking to see how the pattern, one pattern matches another pattern. And when they match perfectly, that's considered a good match. Whereas if the word future, if I'm holding that against some other part of the newsprint where it says the word government, or it says the word India, that's not a good, that's not a good match. So cross correlation is used to find matches. And in this case, what we're doing is we're taking one spectrum, then we're taking another spectrum. A spectrum is where you take light and you divide it into the colors of the rainbow. These are spectra that you're seeing here, these white dots here, all these white dots here, these are spectra. And these are being taken, and you take one, you take another, and you look to see how much the dots have shifted from one to the other using a technique called cross correlation. And because cross correlation, the reason we're doing this is because we don't want the system to drift too much as we're taking a spectrum. In fact, right now, the green square has drifted out of this purple box, which is not a good sign. It's supposed to be inside. It hasn't drifted very far outside, but it's supposed to be inside. In the meantime, the exposure is nearly finished. You can see out of 1800 seconds, it's finished 1754, so less than a minute to go before it finishes. And right as it hits 1800, you'll see that it'll go from the status saying exposing means it's still collecting light, exposing the silicon detector to the sky. But as soon as it hits this number hits 1800, it'll go from exposing to reading out. It'll now start reading out the information that's been collected on the silicon detector. And as soon as that happens, I'll switch screens so you can see what happens when the thing is read out and what the spectrum looks like. So 10, 9, 8, 7, 6, 5, 4, 3, you're counting down to 1800. And as soon as that happens, you'll see this says reading out. Gone from exposing to reading out. And I'll switch screens so you can see that in this window that looks gray, you'll see a spectrum of the stars in the Andromeda 18 galaxy that Evan has just taken a spectrum of. And Yael and Aparajita, this is a DEIMOS spectrum. This is a spectrum, a spectrograph that you have used. And to the students at Future Hope, this is your first time maybe looking at this instrument and this telescope. But come next summer, I'm hopeful that some of you will be so interested in the science that we can involve you in a research project in the same way that Yael's been doing this summer, right? And Yael, next summer, you're welcome to come back to SIP. You'll be a rising 12th grader then, as will some of the students in the Future Hope School.
readout complete.
The readout is complete, and you'll see that this pattern has changed. Did you see how these patterns have changed? This pattern over here. Now, if you look very carefully, along each of these vertical bands, at the center of each vertical band is a very light streak. I mean, I'm running my cursor along one of them, where my cursor is right there. Evan is, I'm not controlling the screen, he's controlling them. So he's changing the contrast and the brightness so that you can see those streaks a little better. Now, can you see that most of them have a vertical streak? It's very faint in this one. Very faint in this one, but with a little bit of imagination, you can see that there is a vertical streak going through each and every one of them. Vertical streak of light. Oh, do you see a spot? One of them showed a spot. That was an emission line galaxy in the background. This spot over there, right there. It means it's not a star in Andromeda, that spot over there. Evan, I don't know if you can hear me. But if you can, I'm seeing the emission lines that you're finding. That's
that's what we're looking at as well.
O2, right there.
Are you sure?
Yep. I promise you. No, it's not. It's not. Sorry. Just scroll up because I can see another line here. It looks cut up because of the night sky emission lines. I see another line down here. That's probably H beta O3 then. If you can you pan down on that slit? I bet you'll see the H beta line. Lower down. So if you center on that and actually zoom out, why don't we zoom out? I'm in view only mode, so I can't do anything, but.
What's like the band of emission lines right next to, what you pointed out as O3 and H beta? Because
those are night sky emission lines.
Oh.
That's air glow. That's all air glow. Almost everything.
I remember bright air glow in that region.
That bright air glow is around 8,600 angstroms. That's a very strong set of oxygen.
Yeah.
That's what that is.
Oh, wow.
The accordion feature.
Yeah,
at
right.
8650. Yeah. Evan, are you able to pan down on that slit to see the H beta line, if there is an H beta line? Unless you want me to do it, I can. Evan, is it okay if I go out of view only mode?
Hi, everyone. What we're doing is we're refocusing the telescope because we're not happy with the image quality. So we believe that the weather is better than we're actually seeing. So if the stars look blurry, it's either because the atmosphere is turbulent or it's because the telescope's out of focus. So we're testing whether the telescope is in focus right now.
And Evan, how do you pan? What do I need to do here to pan?
In Ginga?
Yeah, in Ginga.
You can click on this, that thing.
Yeah.
And then drag.
There we go. Another emission line right there. I'm looking for H beta. I'm not seeing H beta. I see lots of emission lines though. One there. I see another one there. That's probably H alpha N2. I see one here. By the way, these emission lines we're seeing are associated with things that we're not interested in. They are background galaxies that are not stars in Andromeda. That we really care about stars in Andromeda. But every time you see these spots of light, rather than vertical streaks, those are things we're not interested in. I'm just navigating around. So you can see the whole thing is very big region, and we are only looking at a tiny region like that that is shown in the small box. If I zoom out a little bit, you can see that that box, the region we're looking at is bigger and bigger. I'm going to go back into view only mode. Evan and Carlos, was I interfering with your cursor use? I'm back in view only mode, so you're.
No, we're fine.
Okay, thanks.
No, we're fine.
Well, you
Okay.
can,
Still waiting for Heather to finish focusing.
it's gonna be nice.
So you're doing a Myra right now?
Yeah.
Okay. Myra, M-I-R-A, is
Exposure complete.
just an acronym for mirror alignment. So the way you focus the Keck telescope is by deliberately taking the mirrors out of alignment and then
CCD readout
repositioning
complete.
and retilting the secondary mirror. And you can see here that you're seeing 36 images of the same star. There you go. This is the actual pattern of segments that make up the Keck telescope. It's not a single telescope. It's a combination of 36 segments, and each segment produces an image of the star that's being used to focus the telescope. There's a segment that's missing at the center. There's a deliberate gap so the light can go through a hole in the telescope and be focused at the Cassegrain focus. Why do you think one set of dots is so large and bright while this one is so small and faint? What do you think is going on? It's a question for any of the students. This is a very bright star. This is a faint companion. Not companion in the sense of they're not necessarily orbiting each other, but they're two stars on the sky, one bright, one faint. So one produces a faint pattern of dots, one produces a bright pattern of dots.
Exposure complete.
And why is, why are the dots not of equal brightness, even within the same image?
CCD readout complete.
Like,
That's a good question. It's a good question. I think it's because the segments are not perfect. Some of the segments are better figured than others. you'll notice that not only is the brightness, but what is varying is the quality of the image.
Right.
The segments are
And it's
slightly
interesting.
imperfect.
Yeah. And it's interesting that it's grouped a little. So like the bright dots are all like grouped to the bottom left, if I'm correct.
Yeah, but that's also partly because
like
the
they
telescope.
were.
The telescope is partly because the telescope is out of focus and they're trying to.
Oh, okay. Yeah, that makes sense.
Sir, I have a question.
Yes, please. Yes, please go ahead.
This which star is this?
You know, I don't know the name of this star. It probably has a number and a set of coordinates, and Heather picked it to use it to focus the telescope. I don't know offhand what the name of the star is. Let me see if I can find it though. It should be in the tel status window.
Yeah, it'll be in the facts. It's a standard guide star catalog used for dimmer stars. We need a star of a particular magnitude to focus properly.
So this star has a name of S23012 plus 4506. You see where my cursor is? That's its name, or that's its number.
S23012
That's right. That's right. And they're actually the coordinates. So 23012, those are the longitude of the star, and then the plus 4506 is the latitude of the star. I'm using longitude and latitude, but it's the corresponding coordinates on the sky. Latitude and longitude are used for geography and for marking positions of cities and towns on Earth. These are used to mark positions of stars in the sky. The real names are right ascension. I'll write this in the chat. Right ascension is the longitude, and it's written by the Greek letter alpha, just there. And then this is called declination, which is like latitude, and written by the Greek letter delta. By the way, notice these streaks. Do you know why these streaks are happening? Any guesses as to why are you seeing these streaks? It's because the telescope is moving. So the same star, its light is getting spread across different parts of the silicon detector. Now this telescope has stopped moving. It's fixed onto a star. Now you see you don't no longer see those. Now you're seeing streaks again because the telescope is moving. Now it's stopped again. The image quality looks very good, Evan and Carlos. I mean, just from this image, it looks like things have tightened up quite a bit. Heather, what is the seeing, and Myra?
So the seeing is about 0.8 arc seconds.
Okay, so significantly worse than the 0.5 we had at the beginning of the night.
All right, you guys are in position now. I have it set up to where we were before the mirror.
Hello, everyone. We just finished the telescope focus. The telescope was pretty much already in focus, so it was the weather that was causing the bad image quality. We are now moving back to the field we were originally on. We have to realign onto our field so we can put the stars in the right places. And after we do that, we'll start exposing again to get another image of the spectra.
And will you do a coarse line only?
We did not.
Sorry, only a final line?
On a final line, no.
Okay. I'll move to that screen so that we can see how a final line works. You'll use the slit mask alignment tool, presumably.
Yep, we're about to get the first readout from that.
Perfect. What you'll see in each of these pairs of black boxes on the left are intensity
CCD
cuts
readout complete
across brightness versus position. And you see these peaks. The peaks are all well centered, and that tells you that things are well aligned. You can see the image of a star. The box, the little box in which you saw the image of the star, that's 4 arc seconds by 4 arc seconds. Remember, I explained what an arc second is. You all know what a degree is, and 90 degrees in right angle. An arc second is 1/60th of 1/60th of 1 degree is an arcsecond.
Maybe that kind of spiking.
The full moon, every time you look at the full moon in the sky, its diameter, not its radius, its diameter is about half a degree. It's about 30 arc minutes.
I mean, I'm trying to come up with an explanation.
Tomorrow night I might stay longer on 6822.
Wait until Andromeda is a little bit higher. Yeah.
I'm always very optimistic about.
Evan, did you say you want to stay longer on and 18A or longer on Barnard?
I think tomorrow night I want to stay longer on Barnard's Galaxy because we started a little too early on.
Yeah, it was very bright. Sky was bright. We'll have an RLR for you at the beginning of the night tomorrow, definitely.
Okay, yeah.
That's what Yael's studying, actually. She's studying the pulsation of these RLR.
So Raja is pushing for Yael to get some time on the Keck telescope right
yes. Twilight time. Pre-12 degree twilight time.
Heather, can you mark base here? It's a more offset, but just to.
Great, mark base.
Thank you.
Thank you.
So they're just starting a new set of exposures. And you can see that here, 1800 again. But it hasn't started yet. You can see that the status is idle. It's getting ready. As soon as this green box moves into the circle, it's trying to do that. As soon as it moves into the, not the circle, the central square. As soon as it does that, the status will go from idle to starting the exposure to, it will start collecting light. And this green box is all about lining things up perfectly, lining this purple rectangle is half a pixel on a side. Almost there, overshot again.
There's millimeters.
Heather, the 0.02 change in focus, that's millimeters, is that right? So it's like 20 microns.
Yeah, something like that.
Okay, thanks.
So
is that a negligible change in focus?
Yeah, it's negligible. We were asking how much did we have to move the secondary mirror of Keck to get it into perfect focus, and the answer was only 20 microns. That's 0.02 hundredths of a millimeter. Keep in mind that the Keck primary mirror is 10 meters big, and we're talking about motions of 2/100ths of a millimeter.
And this is for the secondary mirror, which is also over a meter in size, right?
That's right. So the way you focus the telescope is you can move the secondary mirror closer to or farther away from the primary, but the amount of motion we're talking about is much less than 1 millimeter.
Wow. And I want to explain what a primary and secondary mirror are. So what happens here is light from a distant star, first mirror it strikes is called the primary mirror, and that's the one that's made up of 36 segments. Because those segments are curved, light from a very distant star, even though it comes in as a parallel beam, after striking the primary mirror, it starts to converge towards a focus. And before it can converge, it hits a secondary mirror. And that light then bounces through a hole in the primary and goes into what is called the Cassegrain focus. But before going to Cassegrain focus, it gets picked off by a side mirror that sends it to what's called the Naismith focus, and that's where the DEIMOS instrument is located, off to the side. Am I right? Is that where DEIMOS sits? Naismith focus, right? NASMYTH, named after probably an optics person who came up with that design. And is Cassegrain also named after someone? I think it is, right? Coude means elbow because of the bend, but I think Cassegrain.
Yeah, I think it's named after somebody. Yeah, DEIMOS sits at right Naismith. We can put instruments on the right or the left side, and we even have some bent positions where we can put extra instruments on the mirror ring.
Yeah, that FCS green box seems to keep drifting out of where it should be, and is that what's generating the cuckoo clock? Back inside now.
Yeah, it is. I wonder if those parameters are a little too tight. Like maybe we should give it a little more, but that just warns you if it's really far out, it doesn't come back in, you need to check on it or call somebody because something isn't working right.
I'm going to step away from my computer for a moment so I can go get a plate of food. In the meantime, please, for the students in Future Hope, are you able to remain connected for longer, or how are you doing time-wise? I hope you're not missing classes on account of Shadow the Scientist.
Okay, that we are here for about 15-20 minutes more?
Of course. Okay, for us, absolutely. I want to give you the opportunity to ask questions. I know that...
Jasmine, how big are the star? You have a question?
The star you were showing to us, how big was the star? Is the star?
How big is the star? That's a very good question. The star that we were focusing on, I don't know if that's a giant or a main sequence star. It's probably a good guess that it's about the size of the sun. And the sun's, let me see if I can do this in my head quickly. The sun, half a degree. Sorry. The sun is about 1 million kilometers in diameter, if I'm doing my math correctly. Evan, do I get that right? Evan can check me. The sun is, I believe, a little over 1 million kilometers in diameter.
Yes.
And it's 150 million kilometers away from the Earth, and it subtends half a degree. And a half a degree is about 1/20th of a radian, 1/15th of a radian. So it's about 1.3 million kilometers. That's how big a typical star is, a star like the sun. Does that answer your question? 1.3 million? I tried to do that in my head, and Aparajita, are you able to do a Google search on the diameter of the sun in kilometers?
Okay.
Yes, 1.39.
1.39. Okay, thank you.
Yes, yes.
But I'm not too far off when I said 1.3. Now, I don't know, to be honest, I don't know whether that star is exactly the same size as the sun or bigger or smaller.
I was using the GSC, the Hubble Guide Star Catalog, so whatever general range they tend to use.
Yeah, so its brightness we know, but I don't, it depends on whether it's a red giant or a main sequence star. If it's a main sequence star, again, it could be bigger or smaller than the sun, depending on its mass. But ballpark, millions of kilometers. Much bigger than the Earth. Yeah. The Earth's diameter in kilometers is about 13,000 kilometers, 13,000, whereas the sun is 1.3 million, 1.4 million. The sun is much bigger than the Earth.
And of course, this is like a extremely difficult thing to measure sometimes, how far away stars are and how big they are. So yeah, we sometimes actually send out satellites in space to measure exactly these parameters. If you want to look up, some of the names are Hipparchus and Gaia. I will put that in the chat.
And in fact, Aparajita, just to build on what you said, once you know how far away a star is, then you can see, and it's difficult to measure that. Once you measure that, and you know how bright the star appears to be, then you know how bright it really is. Once you know how bright it really is and its temperature, you can infer the radius just from the black-body formula. You can infer its radius pretty well from that. So let's just put something in the chat, the names of 2 astronomy missions. They're Hipparchos and Gaia. For the Future Hope students, is it lunchtime now? It's 1 o'clock for you now, right? Yeah, please go ahead.
Do you know what's the age of a star? I know that the brighter one are the young ones and the darker one are old. And when a star dies, it's about to die, expand, and then supernova happen. But how do you measure the age?
You know, it's very difficult to measure the age of a star. It's not easy, especially if you have an individual star. It's very difficult for us to measure the age of an individual star. This is one of the harder things to measure in astronomy. When you see stars in collections, in groups that are together in one point in space, and when they all have the same age, that's typically what happens when you see a group of stars that are all clustered together. They all have the same age. And when they all have the same age, but they have different masses, then it is possible to use the brightnesses and colors of the stars to infer the age of the entire family, age of the population. So I'm not giving you a very clear answer because you've actually asked a very, very good question, and it's a highly technical question. So to determine the age of a star is not easy. It is really have to, especially for an individual star. And you're right that when stars get older, they do bloat up. Not all stars explode. They have to be, only the massive stars explode. The less massive stars don't. The sun is not going to explode. It's going to expand, but it's not going to explode. It's going to expand, lose its outer layers, and then gradually cool down, but it won't explode. Go ahead, please. You've got another question? Yeah, and actually, you know, the audio from Future Hope is very good. When you hold the microphone close, it's very good. It's when you're speaking far away from the microphone that it's a little harder to hear. But go ahead, please.
I had a question. Like in your screen, we could see the temperature, the wind speed. So, like, what is related with weather forecast also?
Yes, very good. They're on this screen over here, right? Is this the screen you're talking about?
Yes, like the humidity, the temperature. So your work is also related with weather forecasting.
It is. You know, it's here's why. The telescope is a very, very expensive mirror with extremely expensive, and it has very fragile coatings on it. So we can't afford to let any condensation happen on the surface of the mirror. You know, the mirror is housed inside a big building, but the building has a big door that's opened up. The building is called a dome, but we have to open the telescope, otherwise it can't see through the metal dome, of course. And it would be too expensive, and too much light would be lost, too much distortion would happen to make the dome out of glass, right? So it's made out of metal, but we have to keep track of the weather. Whether the humidity is low or high is very important to us. What the temperature is very important to us, because you don't want snowfall, you don't want rain, you don't want fog. Yael, you mentioned smoke from wildfires, from volcano. You could get ash. These are all things that have to be monitored very carefully. So we don't care about the weather for the weather's sake. We care about the weather for the sake of protecting the telescope. Does that answer your question?
Thank you, sir.
Thank you.
So I have a question.
Mm-hmm.
Which is when we have finished a research about a star and we just want to like a new star, we start to take a research that how do you understand like what is the difference between the stars?
I missed a little part of your audio, but is your question, how can you tell the difference between different stars? Is that your question?
If I have finished a research about one star, I'm going to research about the second one. Like, how could I distinguish the difference between them?
Absolutely. That's a very good question. Okay. So stars could be different in ways that have to do with how we measure them, but they could also be different in ways they actually are. So intrinsic properties versus measured properties. So two stars could look, you could have two stars that are identical twins of each other, but if one is located close to us and one is located far away, they will appear different to us. That's what I mean by an observed property, measured property. Or two stars could be identical twins of each other, but one may be partly blocked by a cloud of gas and dust, in which case that gas and dust is absorbing some of the light of the star. So it will appear like those two stars are not twins. They won't appear to have identical properties. So that's one kind of difference. But rarely do we find two stars that are truly twins of each other. They could have different weights or different masses. That's very common. No two stars have exactly the same mass. They could have different surface temperatures, which would give them different colors. They could have different radii. Radius of one star could be bigger than the other. If all else is equal, if they have the same temperature, but one has a bigger radius than the other, the one with a bigger radius will appear brighter to us if they're at the same distance from us. They could have different chemical composition. These are all things that can be studied about stars. Their distance, their radius, their temperature, how much light they're putting out, what their chemical composition is, that is the chemical composition of their outer layers. These are all things that can be studied and are studied by astronomers. Does that answer your question a little bit about what kind of properties can be different from one star to another?
Yes, sir. Thank you.
Thank you. These are great questions you're asking. You're all not just future Hope students, you're all future astronomers.
Sir, I have a question.
Yes, please.
Sir, the stars from Earth is light many light years away from us, right? And it takes time to light from here. That means that what we are seeing from Earth is the mass of the star, right?
Your audio is cutting out a lot. Can you speak closer to the microphone, please?
From Earth, we are seeing the star. The stars which we are seeing is many light years away from us.
That's
and
right.
light takes time to come to us. That means what we are seeing is the path of the star.
Very true. Very true. In fact, yes, sorry, did you have more to your question?
Yes. My question is that what you all see from the telescope is the present, or you all see the past? Because the telescope has much high power from our.
Even though the telescope has more power, it doesn't change the amount of light, amount of time it takes for light from a star to reach it. So it is also looking into the past. In fact, if we think about it together for a moment, you're hearing me speak right now, right? And I'm hearing you speak. You're hearing me speak in the past because sound and light take time to travel. The speed at which there's a slight delay in Zoom. When I speak, by the time you hear me, there's been a fraction of a second that's elapsed. Even if I was sitting in the same room as you, if one of your classmates turns to you to speak, that sound and the light from that person, you're watching that person's lips move as they speak, that takes a finite amount of time to travel to you. We can never experience the present. We always experience the past, whether it's in astronomy or in our everyday lives. There's always finite time it takes to hear something from when it was said or to see something from when it happened. So telescopes look very far into the past because the things that it looks at are very far away. Light takes proportionately longer. Light travels at a fixed speed in vacuum. So the further away something is, the longer it takes to travel. Now, I hope I've answered your question. The telescopes are also looking back into the past.
Sir, I have another question for you.
Yes,
I want to, excuse me. I want to ask.
Sorry.
Go ahead, Evan.
I'm asking that has given out the energy and the light, and we can see it after many light years. Okay, so is it possible that the light which has been given out by a particular star is now extinct because it has given out energy and now it cannot? I mean, it might extend also. Is it possible?
Technically, yes, it's possible, but the life of a star is very, very long compared to the times we are talking about here. We are talking about light traveling for, the star we were using to focus is, a few light years away, or the stars in Andromeda are 4 million years away. You said, Evan, light years away. Andromeda 18. 4 million years is a very short time compared to the lifetime of stars in Andromeda 18. Those stars live for close to 10 billion years. So, so unless we were exceptionally unlucky and the star happened to be, in fact, we know that the stars in Andromeda 18, unless they happen to have formed exactly 10 billion years ago, and it's very unlikely that the star has actually disappeared in the time that it took light to travel from the star to us, because 4 million years is a blink of an eye compared to the overall lifetime of the star. Evan, do you agree? Is that a fair answer?
Yeah, that's
yes, sir. But I want to ask that how can you be so sure that the current star is existing? I mean, it can be the light that is coming to us.
You can, but look, Andromeda 18 is a collection of many, many stars. We know that the stars are old, that the stars are long-lived. They live for about 10 billion years. And the universe has been around for more than 10 billion years. But the fact that we see all these stars, we have to be exceptionally unlucky for the stars to have all gone extinct in the time that it took for the light to travel from us. It's like saying people live for 100 years, roughly 80 years. If you saw someone outside your doorway 5 seconds ago, and you haven't seen them for the last 5 seconds, what are the chances that they're still alive? Very, very high, right? Because people live for a very long time compared to the 5 seconds that's elapsed between you last seeing them and now. So yes, there's a small chance someone reached the end of their life either through an accident or some natural cause, but it's very, very unlikely. So when we have small lags in time compared to the average lifetime of a human being, chances are, even though you haven't seen them for the last 5 seconds or 10 minutes, chances are they're still alive. Same analogy for stars. They tend to live for 10 billion years. So even though the light is only 4 million years old, chances are they're still alive. Does that help?
Sir, I have a question.
Yes, please.
Sir, as we know that we see the past of the star, so something block the light of the star coming towards us? Like we are viewing the past of the star and the light is coming towards, if a rock block that star, so we are able to view that star or not?
Not sure I understood your question. You said we are viewing the past of the star. That's absolutely correct. What is your question again, please?
So if the light comes and something blocks that light, so what happened at that time? We are able to view that star or not? If something blocks the light.
If something blocks the light, what do you mean by block? You mean something near the star blocking its light, or something near our telescope blocking the light?
The star.
Near the star. Look, that can happen. There are stars that have, a cloud of gas or dust between us and the star. That can make the star look fainter than it actually is. It can make it so faint that we can't even see it. That does happen. if you look at, if you go out into the night sky and look at the Milky Way galaxy, you'll see that parts of the Milky Way look dark because there are such dense clouds of gas and dust that they're blocking the light of the stars that are behind them. So yes, the light of stars can be blocked. In fact, the light of our sun can be blocked on a cloudy day, right? You go out on a cloudy day, you can't see the sun because the clouds in our Earth's atmosphere have blocked the light of the sun. So the same phenomenon can happen to stars.
So, sir, due to this, due to this, sometimes we can calculate the star wrong. Means the stars measured.
Absolutely. In fact, that's a very, very good point. It took a long time for people to realize that there are these clouds of gas and dust that make stars look fainter than they actually are. And for that reason, they thought our Milky Way galaxy was much bigger than it actually is, because a star can look faint and look far away if you don't account for the fact that there could be dust blocking the light of stars. Yeah, so this has led to past mistakes in how big people have thought our galaxy was. That's not the only reason they made a mistake. Yeah, thank you. Thank you. That's a great question. And sorry it took me a long time to understand and answer your question, but it was a great question.
I have a last question. It's related to black holes. Okay. Actually, we all know the science that if we throw a light of beam, it's go straight. But this science does not apply in black hole. It's go around through a black hole and then enters the black. Is it true?
You know, black holes can trap light, yes. Yes. But it depends on, obviously, a single black hole doesn't trap all light in the universe. Otherwise, I wouldn't be able to see you. You wouldn't be able to see each other. So black holes have a range of influence. There's a region around a black hole from which light cannot escape. Right? So the more massive a black hole is, the larger its region of influence. And this is called its event horizon or its Schwarzschild radius. So the size of the region over which a black hole can trap light depends on how massive the black hole is. But yes, in general, black holes are able to trap light. But if a light ray is traveling at a much greater distance from the black hole than its sphere of influence, then all the black hole does is it bends light. It doesn't completely trap it. Is that what you were asking? Does that help answer your question?
Yes, sir.
Thank you.
Okay. One last question. I think there's a burning question. One last question.
Like, what's the exact difference between a star and a shooting star?
Oh, they're very different. They're very, very different. A star is a ball of gas, typically hydrogen, that is burning, shining because there are nuclear fusion reactions going on in their interior. And a shooting star is a streak of light across the sky, but it's not really related to a star at all. There's no ball of gas. There's no nuclear fusion. What instead happens is a small particle, could be the size of a pebble, could be the size of a grain of rice. A small particle, solid particle, enters the Earth's atmosphere at a high speed. And because of the friction in the air, it burns. That friction causes that particle to burn and produce light. And in fact, soon the particle burns out completely. There's no particle left after a while. That's seen as a shooting star by us. Shooting stars are often called meteors. And if it's a big enough rock and part of it survives the burning and strikes the Earth, that piece that strikes the Earth is called a meteorite. But the shooting star itself, the part that burns, that phenomenon is called a meteor, M-E-T-E-O-R, meteor. These are excellent questions. I know you have to go off soon to have lunch. Lunch is important. I don't want to get between you and lunch. But we will certainly meet again on Zoom and then in person. And I'm so grateful to you, Sujata Di, for making this connection and taking this time to spend this time with us. I mean, even though you're halfway around the world, you seem like just one room away, because these have been great questions.
It's so nice to meet you, and thank you so much, Raja. I think the children are going to call you Raja Sir. So thank you, Raja Sir.
They can drop the sir. They can absolutely drop the sir, and I'd be perfectly fine with that.
Okay, it's up to them. Thank you so much. I have one last question, and you can answer that anytime you want. If you could give us some suggestions of books that we can buy for the library, that the children can read and learn more about what you are saying in these sessions, we'll be very happy to buy those books.
I'm going to do one better than that. My wife is going to be traveling to Kolkata probably in late October, November. I'm going to send some books.
How nice. Thank you so much.
Thank you, sir.
Thank you. Take care.
Bye, everyone. Bye.
Bye.
Bye, everybody.
Thank you for coming.
Bye. Bye.
Good night.
Bye. Take care. This was my first time meeting the school students, and I met their teacher once on a Zoom call, and I met with the classroom for about 20 minutes right before Shadow the Scientist started. But they were completely fearless, and I love that about them. They were completely fearless about asking questions.
Yeah, it's wonderful to see how many they had. It was pretty cool. Nobody just sat there quietly.
Yeah, you're seeing a small fraction of the school. My understanding is they go from kindergarten to grade 12.
Oh, wow.
Been running for 35 years. They are they're expanding to other campuses. So it's a combination of a school and a home. So they have, the way she explained it is right now they have 4 homes for the students. So it's residential in that sense. And but one of the homes is in the same building as the school, but the other 3 homes are in other locations in the city, not very far away, but other locations. So those are like the residential components of the school.
Exposure.
And then there's the classroom or the library they were sitting in. This has been going for, one of the students said 31 or 32, but when I spoke to Sujata, she's the CEO of the school, and there's the teachers and principals there. She said 35 years is how long it's been running. So since 1987. Wow. You wouldn't know it from talking to these children, but they're absolutely from the most difficult of circumstances. From the poorest of the slums in India, from rescued from, in some instances, from really, really dire circumstances like human trafficking and extreme poverty. And
DCD readout complete.
So they receive, of course, they get a lunch at school, but you'll notice the children were in uniform, and that's very common for schools in India. But so in terms of clothing, and it's a wonderful organization. I didn't know about them before. I found out about them only a month ago when I was in India, and I didn't know the CEO before, although turns out we unearthed some mutual friends and contacts, but I didn't know her personally before.
That's a small world. That happens a lot.
I was just blown away by the kids' confidence. She had told me that these kids are they're very good at sports, and this is a big part of the school's identity, is excellence in sport. And a variety. They mentioned rugby and rowing and basketball. I went to a very a school with many well-resourced children, and they thrash my school at every sport that you can imagine. So I was very happy to hear that.
Oh, wow.
Yeah.
35 years. That means the oldest graduates are my age, probably.
Exactly. The oldest graduates have, they're in the workforce. Yeah.
Wow, that's amazing. I'm glad they have that there for them.
Yeah.
And that they're maybe not so glad they're thrashing your school, but you know.
I'm happy. I'm actually very happy to hear this. No, they're really quite a remarkable effort on the part of the school. Aparajita, I'll see you later. Take care.
Oh, you'll have another session in a few hours, I think you said.
In quite a few hours actually. Let's see. It's approaching 1 o'clock here in California. It's approaching 1 o'clock. Hell, you should be asleep. You have school tomorrow, right?
I start school like 11 a.m. every day.
I see.
I'm fine.
Still late for you. So yeah, it's 1 a.m. in California. At 6 a.m. in California, we'll start our next session. So the next 5 hours, we won't be running any sessions, but 3 a.m. Hawaii, we'll get on for a bit.
All right. So you'll wait until close to closing. All right.
Exactly. We had basically the first 2 hours. The last 2 hours is what we've set up. Now, it's also, it was a small group of connections, Zoom connections, but there were quite a few people connected to that one connection at Future Hope.
Okay. Excellent.
So, Prof. Raja.
Yes, Dr. Shipa.
You were saying that this Andromeda 18A. You are saying this A is a link to the element you were isolating to identify the star or something. Can you elaborate a bit on the A part of the name?
Oh, the A part of the name. Thank you. I absolutely can do that. So Andromeda 18 is the name of the galaxy. And every time we use the instrument, we identify which stars we are going to make measurements of simultaneously, right? So we identify a set of stars that whose spectra we're going to measure at the same time. And the way we do that is we design, I'm using that generically, in this case, Evan designed this mask. So once he identified the locations of these stars on the sky, he then designed a metal plate in which there would be cuts made at the location of each of the stars, whose spectra we're going to measure at the same time. That is called a mask, M-A-S-K, metal plate with cuts in it. And the particular mask that he's using now is called Andromeda 18A. He has an 18B, 18C, and each of those target different stars in Andromeda 18. So it's just a naming scheme with that name is associated exactly which stars in Andromeda 18 are being observed.
Oh, okay. All right. So I didn't see nicely what is on the T-shirt.
Oh, that's the name of the school that I was in Molokai. It's called the Akaula School. Sorry, let me move this aside. It was a gift from the school. Evan has one of these too. It's a picture of a waterfall, right? It's a picture. I can't point to my own. There we go. There's a waterfall, and there's a person who is kneeling and praying. Oops. Right in front of it. Vicky would have to explain the significance of this, but there are beautiful waterfalls on Molokai, and I have to ask her about this. This is the school's, I'm guessing this is the school's logo, and I have to find out what it means.
Oh, where is it?
In Molokai, on the island of Molokai in Hawaii. This is where Vicky lives. She runs the school.
Oh, do you know the direct meaning of that name? You said Molokai.
Heather, do you know the meaning of Molokai? I don't.
Sadly, no. Sadly, I don't know off the top of my head.
All right. No, thank you very much.
No, thank you. All right, it is past our shadow time, so I will hang up now. Heather, I'll see you on the Polycom. Yael, I have to respond to your emails. I will. I've just been swamped. Will do. You take care. Enjoy school tomorrow. Get some sleep.
Oh, are we gonna look at RLI race stars like in the next session, like in the California morning, or next session California night?
I'm not sure. Maybe in the morning, but it'll be at the very end.
Okay, sounds good.
After 5 o'clock, after 5 California time. Sorry, after 5 Hawaii time, or around 5 Hawaii time, which is 8 California time. But definitely at when we're going to observe, I'll let you know, because tomorrow
sounds good.
It'll be before the start of Shadow the Scientist. It'll be around 7, so around 10 your time. Today you started at 11, right? So it would be an hour before that. That's when we'll observe the RLI.
Sounds great.
Okay, take care.
You too. Good night.
Bye, everyone.
Bye. Thank you.
Bye. Thank you so much. Please pronounce your first name for me, Dr. Shripa. Is it Moletiani? Moletlani?
Oh, you pronounced it much better than the surname.
Moletlani.
Yes. Oh, wonderful. Yes.
Please say it for me so I get it right.
Moletlani.
Moletlani. Okay.
Yes. No, you pronounced it perfectly.
Thank you.
Yes.
All right. You take care.
No.
Bye.
Later.
See you later. Bye-bye.